Yeah, step up, step that way a little bit.
Don't you hear the people online
There
screaming?
you go. You're good.
Nice. We good to go?
Yes, sir.
All right. Welcome everybody on this cold night. We have a few announcements for you before we get going. First of all, we just finished 4 weeks with the youth group at Bonham Presbyterian, and they thought so highly of it, they've decided that every January they're going to do 4 weeks of creation and have our speakers come in. So we had Denny Genovese there the first week, and then Zach, and then Steve's been there the last 2 weeks. So that's good. We are in the midst of teaching Monday mornings at the Pillar Foundation. And I think Zach was there this morning. And
Thank you.
and I'll be there next Monday, but that's going to go through April, right? So that'll be going through April. We have a creation weekend scheduled at First Baptist Church of Winfield. If you're not familiar with Winfield, it's famous for the Eagles up there, but it's about 15, 20 minutes north of O'Fallon on Highway 79. And so that'll be Friday the 20th and Saturday the 21st. A couple other, and the Zoo Day, just a reminder, is coming up April 28th and 29th. A couple things to let you know about our dear brother, Will Bergner.
Who's online? You should say hi to Will.
Hey, Will. Will lost his wife a few weeks ago and has moved to Arkansas. And Will served on our board for how many years, Scott? Scott?
Yeah.
How many years was Will on our board? 30 something?
Yeah, I can't remember the exact.
I should know that, but he was on our board for over 30 years, served as our treasurer, and Scott has taken over the treasurer duties, and just want to thank Will for his years of service to our group. And we're going to miss you. We're glad you're with us tonight via the internet. We have added a board member, and that would be Hannah Klein, who's sitting right here. Hannah is, she's we like to use the word nerd. She's an astronomy nerd. She loves astronomy, and she's given a couple presentations for our group on astronomy. And you are a writer for name the blog again?
The New Creation blog.
The New Creation blog. So you can see some of the stuff she's written on the New Creation blog. And other than that, I think I'll introduce our speaker. Before I do that, let's say a prayer. Okay. Lord God Almighty, bless our time together tonight, that we'd learn more about the awesome wonder of what you've created, Lord God. And we lift it to you. We pray this evening that we would all grow closer to you as we are in awe of what you've done. In Jesus' name, amen.
Amen.
So we're going to hear from Steve Grimes tonight. And Steve, your presentation is
Origin of Life.
The Origin of Life. Am I right that it didn't start in a mud puddle?
Well, that's what we're going to look at.
All right,
No
Steve.
spoilers, Marv.
We've had
Spoilers.
Steve very busy here. He spoke at our last meeting. He spoke at Bonham twice, and he's here speaking tonight. And I think you're going to Pillar coming up here too, aren't you?
I think so.
In a few weeks. He's been on kind of a whirlwind. So everybody, welcome Steve Grimes.
Okay, well, thank you. Thanks, all you people who braved the weather to get here. And let's see if hopefully I can get this to work. Okay, just lost focus. No big deal. How about now? There we go. Don't need the 5-minute timer. There's the topic. Pretty simple. The origin of life. And I can't unfortunately see the red dot on the TV screen here or probably anywhere in internet land. So we'll just keep moving on. What's our agenda? Well, maybe it is to get this into full screen mode. That should be our first agenda item. And will I do it? Oh, yeah. Let's do that. That'll help a little bit because it was a little small there. Anyway, there's our roughly agenda. What are we talking about? Origin of life, a light introduction into chemistry and probabilities, a few definitions, and then we're going to look at some resources that are out there now, the Stairway to Life and Dr. James Tour, and then talk about the goalposts actually moving further away from a solution to this. A couple thoughts. One is this is a perfect talk to sandwich between the systems talk I did last time and the wonder of the cell talk that some of you may have heard of, because we won't quite get into the cell very much because it's just too much at this layer, but it really fits in between the two. What is a system? Why are systems interesting? And what are some of the aspects and facets of systems? That's good base knowledge for we're going to look at tonight. This is probably the most technical of all these talks. And so there's going to be a bunch of big words, or really after here. What my goal isn't to actually get into any real details of the chemistry and all that stuff, is because A, I'm not adequate to do that. But B, it's a lot. There's a lot of new terminology, concepts, stuff. And so the point I'm really wanting to make here is to show you why this is in my top 10 reasons that creation is winning the intellectual argument. This could be in the top 3. It's right out there with dinosaur soft tissue. Origin of life stuff is winning the day for creationists. So I think that's wonderful, and hopefully you'll at least get that. Even if some of the big words just go by and you couldn't hope to spell them or repeat them, that's okay. That's the real goal, and I'm going to put you again some resources that will get you there for background. First, I do have to make it's not a disclaimer and it's not quite an apology, but I did make a mistake last week, and one of our astute viewers called it out, and I appreciate it. When I was talking about systems, talked about how difficult it would be to have a gradual stepward process to understand and develop the migration patterns of birds that fly across the ocean. I mentioned that birds flying in formation conserves energy and jets don't. I didn't quite say it that way. What it is I had read this paper about the different vortices involved, and I just skimmed it too fast. Jets absolutely do benefit from flying in formation. That's the point I need to correct from that previous thing. And I'll probably ask at some point, I'll fix the video that we have out on YouTube to make sure we get that. The correction will come up written while I'm saying the wrong thing. The written correction will say the right thing. So I just wanted to mention that. But it is a reminder, this is an even much more technical topic. And if I wouldn't hold me to every fine detail here, but I think I will definitely get you into the ballpark of some of these things. And I'm going to point you to where you can go if you really like the detail. As I do. I think it's fascinating stuff. Okay, so having said that, we'll get started. Check the time. I want to make sure I'm going to keep this right at an hour or less. And then questions, of course. What is life? It's debatable, like all things, but we do need to know the goal. Where are we talking about the origin of what? And so, life. And what is that? Again, it's debatable, but let's just look at some of these responses to that term. Biological life is what we're talking about, and it's responsive to its environment. It's subject to growth and change, adaptation, adapting to its environment, reproduction, reproducing itself. These are all traits of life. Metabolism, that is consuming some sort of food source, and even if it's a mineral food, consuming some sort of food source, converting it to energy and using it through the course of life. Maintaining homeostasis, which is, think about your body temperature and other things that have to be maintained at a constant, within a range, a relatively constant value. And so a steady internal physical condition. And that's what we're kind of looking at. In a word, it really comes down to cells. Almost universally, not quite, nothing's agreed to across the board here, but almost universally, the cell is the basic deal. When we talk about life, what are we talking about? We're talking about cells, which is why this talk fits really well with the wonder of the cell talk. Here's just one chart that kind of shows this. If you look at where the line from living to non-living, well, you come up from the bottom. You have subatomic particles, atoms, molecules, and so forth, up to organelles, which are components of cells, enzymes, and so forth. Then you have cells, and that's where the line is drawn, living cells. What we know of as life that's indisputably life is the cells, the cellular layer. And of course, this goes on to other layers, which are interesting. What we really want to talk about is how did we get from that non-living part of the side of the line over to the living side of the line? That's what we're after here. If you're the materialist who doesn't believe in God, doesn't believe in any spiritual reality outside of what we can see, taste, touch, feel, then you have to come up with a purely naturalistic explanation for the processes that would get us above that line. We all agree there are chemicals, there's the periodic table. How do we get that to become life? And that's what the goal is. So this word bios, you hear it a lot, it means life. It's the root word for so many things we'll talk about today. Biology, of course, is the science of life. Biogenesis is the origin of life. That's actually a law because we've never observed any exceptions to it. The law of biogenesis, life comes from life, no known exceptions. Everything we've ever observed is life coming from life. But the problem we need to know is, where did that first life come from? If you believe this all started with a big bang 13, 14 billion years ago, and then 4.5 billion years ago, the earth was cooling and somehow rocks and things and other stuff happened, we need to understand this next term, abiogenesis. Where did that original, the first life come from? And that's why it's distinguished from biogenesis. Prebiotic. This is a key idea here. That's if you take the naturalistic history, the materialistic history of the world on face value, there was a point when there was no life, and then there became life. And so when we talk about prebiotic, we're talking about before the life. And the reason that's important is we can't use any of the machinery that we see in life today, the cells, the enzymes, all this good stuff that cells are doing remarkably well. It's not available on a prebiotic earth. Prebiotically relevant means that what we're looking at is basically just chemicals and chemistry, and maybe volcanoes, maybe a warm soupy pond, maybe a vent in the bottom of the ocean, but whatever, we don't have life to help us. We don't have any of these magical, not really magical, but these wonderful enzymes and things that would help us get there. No proteins, etc. And biochemistry, well, that's just the study of the chemistry of life. Organic is another term you'll hear. Organic chemistry, inorganic chemistry. Basically, all life-oriented chemistry is built around carbon atoms, carbon bonding with other stuff. So organic chemistry is sort of the study of carbon atoms and the things that they do. And then the biochemistry is actually looking at the sort of the next level of into proteins and into the synthesis of all these macromolecules that are involved in life. That's where you get into biochemistry, but there's obviously overlap. Okay, so where does life come from? As I mentioned, the law of biogenesis says it comes from other life. And you can get this out of a secular biology book. It'll just say, law of biogenesis states that living organisms can only arise from pre-existing living organisms, rather than spontaneously forming from non-living matter. And who do we want to thank for that? Who's the guy who proved that? Pasteur, right. He basically said, because somebody else had said, look, spontaneous generation is how life comes about. Well, he disproved it by isolating things so that they couldn't be contaminated, and a very clever experiment came up with what we now call the law of biogenesis. Okay, now, the story of abiogenesis, that is life coming from non-living matter, non-living chemicals, I'm going to call it the story of abiogenesis. That's kind of along these lines. You have carbon. We know carbon's going to be involved because carbon's what all life's made of. It's not made of silicone or these other ideas. We know there will be water involved for various reasons, and there's energy involved, and then poof, you get life. And it seems like that's maybe oversimplistic. Yes. Of course, it is oversimplistic, but I wanted to get us started. Here's another picture. This is the same story, a little more detail. You start with a habitable planet. You have prebiotic synthesis. Prebiotic, meaning again, it's like a prebiotic Earth. There's no actual biological chemicals helping with the process. It's just the chemicals themselves. And then they form these other chemicals, more complex chemicals. They call polymers and vesicles. We're going to define a lot of that stuff. To get to your first protocells, to get to LUCA, which is the last universal common ancestor, which this is kind of crazy all in itself, because LUCA then becomes the progenitor of bacteria, archaea, and eukaryotes. And there's such vast differences between these three areas. I'm surprised they just don't have three Lucas, but they have one. Now, there is a Fuca, which is the first universal common ancestor, but that's pre-cellular. It's before Luca. Luca kind of descends from that. That's where you get some components that became the first cell. And this is the population of cells, Luca, from which everything descended. You know, your Darwinian idea of descent with modification. It all started with that first population of cells. I don't know if they're going to shoot for they might as well swing for the fences here. I'd say you ought to have a bunch of different cells. It'll solve problems later than just to say it all comes down to one. But for some reason, it only happened once, only happened in one place, one population from which everything else descended. Okay, here's a proverb that came to mind. The one who states his case first seems right until the other comes and examines it. And I didn't think this is the best place to place this thought, but there is a whole lot of stuff. If you Google any of these terms we talk about, you're at the first page or two or three, and your results set. I don't care, Bing, Google, DuckDuckGo. You're going to see, oh, we discovered this. Oh, we're polymerizing amino acids in water. Oh, we're solving all these your origin of life problems. Article after article after article, reference to paper. It's just over and over. You'd think they're really close. They got this solved. It sounds really good. And that's why I'm putting this verse up there. It sounds really good until an expert comes along and says, well, wait a second, what about this and this? And someone, not me, but someone who's actually an expert in this field, and that's what we're going to get to. One of the first books I read on this topic, and maybe not, at least in the last 5 years, I'm on my third time through. It's a great book. Changed Tan did a wonderful job, and her co-author, Rob Stadler. I'm going to let him introduce this topic. So this is off, again, part of the introduction. There's a Twin Cities Creation Science Association up in Minnesota, and they're like us. They have these meetings, they have talks, and they discuss these things. Well, he's a PhD. He's got, I think his PhD's from MIT, and he also studied at Harvard. He's a very bright guy, very well credentialed. And I didn't put all of his credentials, but you can certainly look him up. Anyway, I think he's an excellent communicator as well, I believe, as you'll see from this video. 3 minutes.
So this book came out in March, right as COVID was getting going. And I wanted to point out my co-author is James Chan, and she is a professor of biology from the University of Missouri. And it was a real pleasure to work with her on this project. So I'd like to start off with something really simple. And that is to say that when a living organism dies, there is a simple process that goes on after that of decay and disorder, which is a one-way process. And we're also very familiar with that. We're in the very complex molecules associated with life and their highly organized state degrade and decay, fall apart and break into smaller and smaller pieces. And this is, of course, very obvious. It's a natural process. It happens according to natural laws. It's directly observable. I'm sure everybody online has observed it. It is universal. It's irreversible. You can't go backward. It's unavoidable. And it is just simply common sense. But to say this is kind of what this whole talk is about. It's common sense, but yet there are a lot of people, a growing number of people, even some pretty smart people who are trying to convince us of the opposite, that you can start with something very simple, like primordial soup, and a natural process will build up very complicated molecules and load them up with information content and highly organize them into structures and lead to a living organism, a very simple living organism perhaps, but a simple organism. And this is called abiogenesis. So in contrast to the previous slide, this process is unobservable, meaning no one's ever seen it happen. It is unnatural, and we'll talk a lot about that and how it doesn't follow natural laws, and therefore it's unscientific, and I would say it's irrational, and it's faith-based. And so that's the end of the talk. We don't need to go any further. The disturbing thing is, as I said, there are a large number of people, a growing number of people and some smart people that really do believe this is going on. So I'd like to give you a little taste of that. We have a good friend, Carl Sagan. And he said that the origin of life must be a highly probable affair because as soon as conditions permit, up it pops. And as I said, this is unobservable. No one has observed it, and yet he can make such a bold claim as this. And what I find really interesting is that Carl Sagan is also famous for another quote, which is extraordinary claims require extraordinary evidence. And certainly this is an extraordinary claim, and there's not a lot of evidence for it. And then we have Jeremy England, who is a physics professor at MIT, and he's now at Georgia Tech, but he's well known for this quote. You start with a random clump of atoms, and if you shine light on it for long enough, it should not be so surprising that you get a plant.
Wow. So that's the beginning of an excellent talk. That's why I put all the details in the previous slide so you can check it out yourself. I appreciated this stuff. Anyway, and I'm subscribed to this site where I get all these pictures. I had to pay for it, so I went ahead and grabbed pictures when I can. This I thought was a pretty picture of chemicals. This is my head title slide for the next section. That was the introduction. Now we're going to look at a light introduction into chemistry and probabilities. Well, let's see where this takes us. First of all, we have to get some basic things down. Again, this isn't to make us chemists because I couldn't, because I'm not a chemist. But I can appreciate certain things, but feel free to send in the corrections later. The atom is, we know things are made up of atoms, and the atoms, of course, are made up of other things, protons, neutrons, electrons, but they make up molecules and so forth and so on. This is what the material world exists of. This is what biological life exists of. It's just a different branch of chemistry, but it's still atoms and molecules. So there's atoms, and they have properties. What's neat about the periodic table, and someday, if I would need a couple semesters of chemistry to really do this justice, but there's tremendous organization and order. The hand of God is in this table. I don't say that lightly. I really think it's amazing the way this is organized and structured. And the colors all have meaning. Like that bar on the right, those are your noble gases like argon and helium. They're happy. They have a perfectly content outer covalent shell that keeps them from bonding anything else. That's why they're noble. They don't mess around with the peasants. They don't bond with things. So there's actually certain parts in origin of life experiments where they will fill up a system with argon gas so that they can carry on other reactions within that so that no other interactions with the gas become, and there's points that with the, so there's just all kinds of structure and beauty here. We won't get into that. But atoms do make molecules. Most of us are familiar with H2O, water, and there's others that just clump together for various reasons that make them happier. And so you have H2 and O2 and N2 and so forth. And these molecules, eventually, they get more and more complicated as we observe things in the physical world. And here we have some larger clumps of atoms. Got some groups over here. We'll just call out. There's four I want to call your attention to. Phospholipids. Those are your fats. And we'll look a little bit at that. We'll talk more about that in the cell talk. There's sugars, and that would include glucose, and it would include other starches and carbohydrates. So sometimes that's just called the carbohydrate branch of biological molecules. There's the amino acids, and those amino acids, they're going to come together to make peptides and proteins eventually. So that's kind of the protein area. So you get your fats, your carbohydrates, your proteins, and then you have your nucleotides. The fourth major category of biological molecules is nucleotides. So three you should have heard of, fats, proteins, carbohydrates. We've all heard of that because, we read the labels and we eat stuff, but hopefully. But nucleotides, you may not have heard of. Of course, those make up the DNAs, the RNAs. And so those are the molecules we're going to make life out of, okay? The amino acids, let's drill in on this. And I'm borrowing some slides from other talks I've done, and sometimes I always find new slides that look more interesting, so I grab those. There are about 20 amino acids. This is 3 of them. All I would call your attention to is that they all have carbon in them. They also have an amine group. They have a carboxyl group. They have a side chain. We'll touch on that. But for now, we just need to know, here's 3 of them. They have a short name, 3-letter name. They also have a single letter name, T, A, and B, and so forth. This is a table of all 20, and they can also be classed They can be organized. And here you see the name, too hard to see from the back row, but there's the one letter equivalent and so forth. Okay, so amino acids are molecules that make up proteins. Now we're going to start to get into a few other definitions. If you've heard all this stuff, sorry. If you haven't, it's okay, but some of this is going to go over, and that's okay too. But we'll start pretty easy. Let's look at a monomer. A monomer, and this is just from an organic chemistry source, a molecule which is capable of combining with like or unlike molecules to form a polymer. Well, mono means one, poly means more than one. It's not so bad. There actually is some sense to all this. It is a repeating structural unit within a polymer. It is also known as a repeating unit, and this is a different way to represent the amino acid tryptophan. Polymer monomers then can be combined to make polymers. Okay, that's not so bad. That kind of makes sense. Polymer, substance made of giant molecules formed by the union of simple molecules. Got the word of twice there. Apologies. A dimer. Well, that's a molecule that a molecular complex consisting of two identical molecules linked together. Okay, you with me so far? Okay, so I'm going to do the first quiz question. What do you think you'd call three monomers linked together?
Trimer?
A trimer. Yeah, a trimer. Right? You're with me. Okay, let's see. I'll take you to the next level. What do you think a 200 mer is?
Centimer.
Well, no, not the name of it. How many monomers do you think are in a 200 mer?
200.
I try to ask. Yeah, 200, right. There's 600 mers, there's 200 mers. Polymers have different lengths, and sometimes they even number the number of monomers in them as they describe them. So anyway, a dimer, a trimer is a polymer consisting of three monomer units. So you have monomers, you have these polymers, which are made up of monomers. That was all. That was just an exercise to do that. Okay, the isomer, this is a little tougher. Isomer is like a molecule that has, it's made up of a series of compounds. The molecular formula will be the same number of H's, same number of O's and C's and so forth. But different arrangements can cause them to have different properties. There are what are called stereoisomers. Now, as you know from the cell talk, I love Legos. So let's pretend these Legos are molecules because it's easier that way for me. And these would be an example of stereoisomers. That is, they look about the same, but they're really not quite the same. These are what are called non-overlapping images. I don't want to jump too far ahead here. So we're going to put these down and keep going a little bit further. But isomers are basically molecules, a little bit more complex. And again, the chemical formula will be the same, but their structure, their three-dimensional shape will be different. Okay. Oops, let's go back to this. So, review the four biological molecule classes: carbohydrates, proteins, and fats, and nucleic acids. The monomer of these, you've heard many of these. Amino acids, well, that makes the polypeptides, which gives us the proteins. Monosaccharides are the building blocks of carbohydrates. Alcohol and fatty acids give us the lipids, which are the fats. And nucleotides give us polynucleotides, which give us the DNA and RNA biomolecules. Okay, and amino acids, as we chain them together, again, they make proteins. Proteins have to then be folded, and their shape is what determines their function, or we can say their function is determined by their shape. And that's some of the props I forgot. I used to take a big bolt, a big nut. The nut would screw onto the bolt. The function of the nut is determined by its shape. So is the bolt. You shape them a little differently. You change the threads a little bit. It doesn't work. But if the shapes are just right, they have a role. They work together. They do something functional based on their shape. Proteins are sort of like this. You've heard of proteins like collagen, like hemoglobin, the oxygen-bearing protein, the insulin. You've heard of many of these proteins. This is one you may not have heard of, lysozyme. But it's just a protein. It has a nice clear picture, and it's a no copyright picture as far as I can tell. This shows all of those amino acids in their three-letter form strung together to make a single protein called a lysozyme. And you have down here the amine group. That's the beginning of this first amino acid. Goes all the way around to about 120, 130. And then you have the carboxyl group, which is this group that spins off that last leucine is what I believe that last amino acid is. And what you can see here is you basically just have a long string of proteins, albeit with some shape and some interconnections, a little bit more complicated than just a string, but it's a polymer. This is a polymer of amino acids. It's 130 mer, if you want. I don't know if that's a word or not, but we could call it that. It's got 130 steps. Okay, how many letters in the alphabet? 26 letters in the alphabet. I think that's the right answer. If it comes up right, you're good. What are the odds of picking an L from a box of 26 letters? If this was a box of letters, and I reached in, 26 letters, I pull out a letter. What's the chance I'll get an L?
1 in 26.
Well, no, 26. That's odds. It's probabilities. Okay, that's the right answer. What are the odds of, if I then reach into the box, I put the L back in, I shake the box again, I reach in, and so it's a fresh start. Everything's a fresh trial. I reach in and pull out a letter. What's the chance of getting an I?
1 in 26.
1 in 26. That's correct. Same as L, 1 in 26. And so the probability of spelling life, you repeat that, is 1 in 26 times 1 in 26 and so forth to the fourth power. This is where exponents come in so handy. 1 in 26 to the fourth power, which is a fairly big number. The chances of in 4 tries me getting life is that. Now, try again. Eventually you may get that, depending on how many tries you're making. Yeah, that's a fairly big number. Here's the question, and if we put that in scientific notation, it's 5 decimal places past the decimal point. So that's 1 over 4.57 to the 10 to the 5th power. That's the same number. It's just represented more sort of succinctly with scientific notation. Okay. Well, those proteins, like the lysozyme, are kind of like words. And let's go with albumin. Let's talk about an average length protein called albumin. This is 585 amino acids. And I'm using the single letter representation for the amino acids that make albumin. Now, some proteins are 1 to 2,000 monomers in length. Some proteins are 60, 70, 80. There's different lengths, but 500 is not unheard of. 3 to 500 is, I don't know what the average truly is because we're discovering new proteins all the time. But, I'm going to put this into my cell talk. There are over 1,000 proteins just in the cell membrane that govern semi-permeable characteristics of a cell membrane that let certain things out. Like the food's got to come in, the poop's got to go out. It's way more complicated than that, but there's over 1,000 proteins that govern what's going on in the cell membranes as they interact with all the other stuff in your body. Anyway, let's take that 585 amino acid polymer called albumin, and let's do the odds on that. Well, if life was roughly that, use our exponents to make it simpler, what would albumin be? Well, we got to do that. There's only 20 amino acids. So first of all, it's going to be easier, right? There's only 20 amino acids, but the word's much longer. And so the multiplication needs to be done. And when you do the multiplication, obviously it goes on a long time. I didn't want to just click. I used to when I was more masochistic in my younger days. But now let's just cut to the chase. It's 1 to the 20th to the 585th power. That's your odds of getting albumin. Now, different mathematicians have known this since the 60s, the Wistar Institute. There was this conference, and they describe all these problems. And there's responses, but I don't think any of them are very good. Mathematicians don't buy them. Biologists do have some responses, but they're pretty lame. This statistical improbability is tough to get around. This is just converting it to a straight decimal number. You'd need a 761-digit number to describe the odds of getting albumin spelled out. That's how many trials you would need. How about winning the lottery? These are old numbers. These are 10 years old. I pulled this up from the lottery website. About 1 in 300 million. Okay. So that's really, in a scientific scientific notation, is 1 over 292 to the 10 to the 8th. Well, how about winning the lottery twice? You just multiply those. And the beauty of the exponents, you just add. So now we're just at 1 over 292 to the 10 by 10 to the 16th. And so therefore, if you do a little more math, you have the odds of winning the Powerball lottery 95 times are better than the odds of assembling albumin from amino acids. So one of the responses to this was, well, yeah, but we have billions of years to work in and we have a big universe to work in. Okay, take every subatomic particle and stuff the universe, the known physical observable universe, stuff it full with the most dense neutron star level density of subatomic particles. Make every one of those a particle that does 1 trillion operations, 1 trillion combinations, 1 trillion attempts per second, and run that for 100 billion years. You still don't have enough time. The numbers just don't get you there. The numbers are so extraordinary far out there that you don't have enough time to probabilistically, using all the probabilistic resources of the universe, to get to these size numbers that we need to form these peptides. So this is one problem with peptide formation, just the number problem. But wait, there's more. This was the dip into probabilities and math. Let's dip back into chemistry. Amino acids, as many of you know, are formed with one exception, come in a mirror or symmetric images. They have left-handed form and a right-handed form. Your hand, right? Your hands are, the word is chiral. We'll come up to a definition screen here in a minute. Kyra comes from the Greek word kyra, means handedness. If I hold this hand in a mirror, forget the Band-Aid for a second, that would give it away. And I'm looking in the mirror, what am I going to see? I'm going to see the palm of my hand. I'm going to see my thumb on this side. And I'm going to see my pinky on that side, right? That's what I'm going to see in the mirror. This is a mirror image of this, right? But this is a non-superimposable mirror image. That's what I didn't want to say yet when I had these up in the air. These are mirror images of each other, but they are non-superimposable mirror images. What that means, there's no way I can make the two just, they're not the same. They really are not the same. They are not just symmetrically the opposite. They are distinct from one another, and they have distinct properties. Well, when you get to these, the peptide or the amino acids forming proteins, they're all L form, right? And turns out the nucleotides are Ds, D form. And there's the Wikipedia page on this is actually pretty interesting. Only L form amino acids are found in functioning proteins. L and D form occur in roughly 50-50 probability. What that means, and I have a demonstration coming later, but if I had a bag of amino acids, and I do, what I have here? These are all my molecules, right? These are the base molecules. Now I shake this bag, and you may be wondering, why is he using McDonald's bag? That's because Burger King isn't on a prebiotic earth. No, that was a joke. See if we keep it up. Anyway, so if I shake this bag, well, I'd have to shake it pretty hard. Let's add a volcano level, earthquake level. Let's add a huge amount of energy. Will I eventually form some, will I get some links between some of these Legos? Yeah, probably. Will I get this? Well, if I shake this bag long enough, in fact, forget this bag. Let's say the bag is the size of this room full of Legos, and I shake it, volcanic level shaking. Will I get, maybe, I might get one. I might get two. And if I get one, then what I have to do is combine it with the next one. If I get one that's the right form, this one's close, not quite. That's the D form. I want the L form. If I get one, then I need a second one so I can polymerize that. So I can put those two together, right? So that's the challenge that's going to have to occur in a prebiotic earth chemically to start to form these peptides and eventually proteins. I got to start putting these things together. Well, whenever they do these experiments, the trouble is when they do form, and the Urey Miller experiments got them to form back in the 50s, little electricity, reducing atmosphere and so forth. They got amino acids. The trouble is they get a mix. Some left hand, some right hand. It's called racemic. And I'm jumping ahead. We're going to do a definitions page and go through this a little bit more closely, but because it's really harder than we've ever thought before. It's even this area is getting trickier. So let's continue. But wait, there's more. Amino acids found in proteins, again with one exception. This further reduces the chances. That's the same slide. Let's go back to the chemical structure of an amino acid. Don't need to learn chemistry here. All I want to call out is a few terms. The amine or the amino group on the left side, you see the hydrogen and the nitrogen. On the other side, you have a carboxyl group. And if you guys have had organic chemistry, I'm sure you could do all this better than me, and my apologies. But the point is, these amino acids tend to have these two groups, the carboxyl and the amine, and they have the side chain, this R side chain, and all I think but one. And so this is why they're stereoisomers. They can form two different shapes and give us an L form or a D form. And when these things are linked together, here's the next problem. They have to link the right way. You have to link them together in what are called peptide bonds. Now, whenever you see those pictures and you got the bars between the C and the O and the H and the double bars, that all has meaning. It all has very important meanings. The peptide bonds are between a carboxyl group and an amine group. So if you got amino acid this one and amino acid that one, you can't just go, oh, I got two. Look, I got a dimer. No. Because the chances are you might get a carboxyl to carboxyl or whatever. You need the carboxyl to the amine, the carboxyl to the next amine. It has to be peptide bonds. Only peptide bonds are in life. The other bonds aren't allowed. So there's another reduction because they form at a roughly 50-50. Sorry, I made this a little small. They form in roughly 50-50 ratio. Peptide bond forms when the carboxylic acid group, and it gives you a little chemistry there, of one amino acid reacts with the amine group of the other. That doesn't even include the side chains. The side chains are that's another problem. Okay, so only peptide bonded amino acids are allowed in these proteins. Peptides and non-peptide bonds form with roughly equal, just like the left hand, right hand, there's roughly 50-50. So again, our statistics are going down. Remember that monster number? Well, let's double it. Remember that bigger number? Let's double it again. These things are even harder than we first thought. And by the way, as I was researching for this paper, I came across this rare photo of an origin of life researcher in his lab. That's the cool. Let your brain cool for a minute. Throwing a lot at you here, a lot of terms. I get that. This first exposure to this would be, but if you've seen it before, you're probably going, okay, get to the point. Sorry, there's a balance of audience here. Anyway, that's the cool. Okay, let's go on with a few more definitions, and then we're going to start to see where these problems are popping up everywhere. But these terms are going to come flying at you, and I want you to have some exposure to them. Hydrolysis, neat term. You've probably heard it before. A chemical reaction in which polymers, larger molecules, you know what those are now, right? Polymers, a bunch of monomers together, break down into monomers, the smaller molecules, with the addition of a water molecule. Water is damaging in this sense. It's a great solvent, and it leads to hydrolysis, which is the breaking down of these polymers into monomers. There's another reaction we should be aware of. Condensation reaction do just the opposite. That's a chemical reaction in which monomers combine to form polymers and a water molecule is released. The problem is polymerization in water is a challenge. And there are papers that are titled, "We finally solved the polymerization in water." It's much more scientific title than that. But, and if you look at the paper, and I can't fully digest the paper, but I've looked at some papers and then heard lectures from some of these origin of life scientists that are calling this out. The way they get polymerization in water to occur, first of all, it won't occur. Water pushes it the opposite direction. Water, the polymerization is a condensation reaction which wants to release water. Well, it doesn't work. The energy levels aren't right for that to occur in water. So therefore, it can occur in water. But other stages of the process need to occur in water. It's called the water problem. There's real issues with water. You need it. It's absolutely essential. You got to have it. And it causes hydrolysis. So what did they do? Well, they have these little hydrophobic pockets. Neat word. It's like a little bubble in the water. Now inside the bubble, it's dry. So technically you're in water because you're inside this little hydrophobic pocket, this little bubble that's dry inside the water. And there you can have your polymerization happen, in theory. And then and they probably have achieved some of this, and I'll get to that in a second. Then you say, hey, look, we got polymerization in water, quote unquote. It's kind of a definition thing, but really it wasn't in water. It was in these hydrophobic pockets that floated in the water. Anyway, a few more definitions, and then I'm going to expose you to some of the, let's pull this all together. Chirality we just talked about. That's your handedness and the non-superimposable mirror image idea. Homochirality, well, that would be all the same. If you have only left-handed molecules, then you're homochiral. That's beautiful. There's some debate and argument about the terminology here. Chiral is not appropriate for all situations. So the other word that gets used, and I'm just throwing this at you because it just gets thrown out there, enantiomeric purity. Basically, this is again a stereoisomer. It has two forms, and when it's all one form, it's pure. And it is roughly the same. I think some definitions, I don't know if it was Wikipedia or whoever, they said it's homochiral. But other chemistry texts are really careful about avoiding using them synonymously. But there's definitely overlap in the terms here, and way beyond my pay grade or my abilities to tell you about that. But you just making you aware of it if you decide to research this a little further. And then what we often see is a mix, the racemic mix, which is something less than pure. And then there's a term called enantiomeric excess, which is how they measure how pure it is, and it's interesting. But if it's 100%, then you're pure, and if it's less than that, you're not pure. If you're 0, you're perfectly racemic because it's a 50-50 dividing line. Anyway, let's do the demonstration here. So imagine now I'm shaking up my bag, and I shake it up really good. That wasn't enough. Create a room full of these. Shake, shake, shake. I eventually get the one I want. Write a paper. Publish it. We have synthesized a biologically relevant molecule in the lab and call it the beginnings of life. The headlines are going to go out. It's big. It's big. Trouble is, what was your yield? You created a lot of other stuff that you couldn't use. Some of these papers have a 1% yield of the molecule they want and 99% of what they didn't want. Uri Miller came up with a bunch of stuff they couldn't use. And the trouble is, you can't go to the next step with garbage. The next step has to be polymerization of a bunch of just perfect left-handed molecules that you're going to form these peptide bonds with. So what happens is this next term, the last term on this slide, relay synthesis. This is interesting. James Tour points this out. I don't know if he'll talk about it in the few minutes video I'm going to throw at you here in a minute. But relay synthesis. So they shake the bag. They come up with the one. Oh, it's very unstable. Did I mention the stability problem? There's a stability problem. Tour's going to talk about that in a second. I'm going to unleash him on you for about 7 minutes. But I got the one I want. Now they go out to the store and buy 1 million of these and say, we formed it in the lab. It's next. We formed it. And now we just need to do the next step. And it's called relay synthesis because they don't use the product of the prior stage. They buy fresh material for each successive stage. Kind of sounds like cheating to me, but then I'm not a scientist. So, but when James Tour calls this out as a problem, I think he's got the credibility to do that. Okay, so is that enough definitions for a while? That was the demonstration. Yeah, I think so. Okay, so now let me point you to some resources, then I'm going to bring you to another video. I found this book excellent, as I mentioned. Rob Stadler, the guy you heard from already in this talk, and James Tan, who's been in our meetings before. So if you ever get a chance to come up and talk to her, I encourage you to do so. Really bright gal. This is an excellent book. It's communicated so well. I think a lot of the story is just told by the table of contents. If we look at some of these issues with, and they don't even necessarily have to be in order, but they're kind of in order, the formation and concentration of the building blocks. Remember, you're going to need a bunch of left-handed formed molecules before you can start polymerizing them. Polymerizing garbage doesn't get you anywhere. You have to polymerize the good stuff. Okay, that means you got to concentrate it. Homochirality, and of course, we just talked about the solution for the water paradox we touched on. Consistent linkage of the building blocks, that's the peptide versus non-peptide, that's 2. There are lots of ways to link things together wrong, and one way to link it together right. Here's another analogy I've used in the past. Imagine, you've probably heard of the tornado through the junkyard building a 747. Or maybe it's a tornado through a paint factory producing a Rembrandt. Why doesn't that really work? Well, it isn't because, the paintbrush spinning through this paint all flying around. It is possible that on the canvas, a paintbrush flying through the air just intersects with the right paint, just the right thickness, just the right amount, and goes across and creates a stroke of what Rembrandt exactly did on one of his great paintings. It's possible that could happen. The trouble is, in that same moment, it's equally possible and likely that all of the ways that it could go wrong are also occurring. It's not just the probabilities of getting it right. It's the probabilities of getting it wrong. So if it's 1 in 100 that you'll get it right, that's still a long shot. Remember, it's 99 in 100 that you'll get it wrong. That's what I find fascinating about those. The tornado that's going to build the 747 is also going to destroy and break down the 747. So many of these forces involved at this chemical layer are destructive, like hydrolysis, like oxygen, very destructive, except in the right spot. So anyway, biopolymer reproduction, that's self-reproducing molecules. Of course, the Origin Life people claim they've done it, and they've been called out on this. Stadler has a whole separate talk on that. It's really good. Basically, they took one full macromolecule. They took a second mirror image of it. They cut it in half. Basically, put it in the bag. Put it in the bag together, shook it long enough, and guess what? Some of those halves reformed. They also did some games to make them attracted to each other just the right way. And so some of those halves reformed. They called it self-reproducing RNA. It's like, what? I mean, the definitions are, but you don't get, the title looks great. The details is the problem. And another one of these papers that we mentioned on a page I won't even probably show you too well. The yield comes back to that yield issue. So they had this self-reproducing RNA in the laboratory, but the errors that occurred. So if, let's say it was a 14 mer or a 20 mer, and then in the next step, well, about 12 of them made it. 8 of them were wrong. And the next step, and seriously, in just 2 to 3 to 4 generations, they had replaced so many of the base nucleotides that it was totally not what they started with. This is why you have number 8, means for repairing biopolymers. Your body's doing that. It's absolutely necessary, especially with RNA, which is much less stable than DNA. Remember, DNA is the double-stranded helix. RNA is split that apart. It's a much less stable polymer. Anyway, all of these things are important. My favorite is the means of harnessing energy, but I'm just going to have to put that in talk by itself. That's the whole mitochondria and the proton gradient and all that stuff. A little bit of that is in the cell talk. So I encourage you, if you have any interest in this topic, this is a great book. I gave it one copy to all my kids, and then I read it again. Now, let's talk about James Tour for a minute, and I'll start to get us to the wrap-up here. James Tour is a first-class, world-class scientist, and some of his studies, professor of chemistry, of nanotechnology. I should just read it probably. Professor of computer science, professor of material science and nanoengineering. He's the head of many different centers. He's at Rice University now, and really outspoken and excellent. 800 research publications. That's a lot. That's peer-reviewed publications that he's authored or co-authored. A lot of his names on them, but it's being done in his lab. It's being done in the auspices of his people. 140. This is the real interesting. Anybody can write a paper. This happens a lot in the social sciences. People write papers, but then they go onto a shelf. Nobody cites your paper because A, they can't replicate it, and B, it's not that valuable. He's got 140 citations of his work. And this H-index, which I don't understand, that's apparently pretty impressive, the H-index of 175. That's for an academic, that's pretty high. Based on the impact of his published work in 2019, Tour was ranked in the top 0.004% of the 7 million scientists who have published at least 5 papers. He's a serious guy. He's got 130 plus patents, and it goes on. Let me give you a little bit more here. Tour scientific research areas include nanoelectronics, graphene, electronic silicon. He's created like 6-7 companies that have been built around the patented work he's produced. Silicon oxide electronics, green carbon research. This is the real deal scientist. This isn't the academic who makes speeches or the guy like me who's just a consumer of knowledge and likes to relay it to other people. This is the guy who's doing the work and in his lab, and that's why he gets millions of dollars to do this work. I just highlighted some of carbon composites, nanoscale antioxidants. He's built these little nano cars. They race these nano cars. Pretty neat. Little molecular cars, and they race them. And they've won. His team has won. I don't know if they won every time, but they do it like every year or two. They have these races. Nanoscale antioxidant synthesis of single molecule nanomachines. This is a guy who understands what it takes to connect one molecule to another molecule inside out. And what I'm going to show you is he's going to challenge the Origin Life people to talk to him about the chemistry. You can put your fancy titles in your papers. Let's do the chemistry, and they won't answer them. They will not respond. You'll see this. Single molecule nanomachines and so forth. Okay. So let me grab 5 minutes of an introduction. I think this is, I've probably watched 20 to 40 hours of Tour stuff. And I think this boils down to the best 20 minutes of it. It's that when he went to Harvard and they finally said, okay, we'll let you come to Harvard and do a talk. We'll do this roundtable discussion. We're going to have, we'll invite some other Origin of Life researchers. The only one that answered is Lee Cronin. Lee Cronin comes. I give him credit for coming. Most of them just, they won't do it. By the way, James Tour is not, he's made speeches with the intelligent design people. He is not a follower of intelligent design. He's not a young earth creationist as far as I can tell. In fact, he has said repeatedly that he thinks science will solve the origin of life problem. But he's just saying we're not even close. We're not even beginnings of beginnings. And that's his real point. Now, because he's also an outspoken professing Christian. I mean, I've seen him do lectures where he'll be lecturing a crowd and he will just step outside from behind the podium, kneel down and start praying to Jesus for the people in his audience. I mean, the guy he's powerful. So, and if you don't like that sort of thing, well, then you might not like him, but you can't argue his scientific credentials and the way what's going on upstairs. So yeah, I'm going to take 5 minutes of this 20-minute introduction where he balls it all down. It's like a machine gun. He gets his 20 minutes in front of all the Harvard people. They got the biochemists here. They got the chemists, the physicists, and organics. All these PhDs sitting in this room. He lets them have it. And then it's followed by, this is like a 2-hour video. It's a 20-minute intro. Then Lee Cronin does a 20-minute intro. And I'll give you a little bit more. He predicts Lee Cronin's not going to touch the chemistry on this. And he was right. Lee Cronin never brings up chemistry. Because why would he? He's in the room with James Tour. He's not going to do it. And then he says, and I also agreed before they let him come, he can't talk to anyone. He can only sit at the table and answer any question that's asked of him. And nobody asks any questions. This is how the state of affairs is in this area of science. It's pretty remarkable. I encourage you to watch the whole 2 hours. I may be coloring this a little bit, but I'm not coloring it much. This is basically what goes on. And then other conversations that he's done with other people is where he's mentioned, yeah, these were the rules. Everybody asked him, why didn't you say anything? Why were you sitting there so quiet? He says, because I made a deal. I wouldn't open my mouth unless I was directly asked a question. So he sits there for the rest of this time. And it's really kind of a shame. But boy, the open in 20 minutes. This is storm the beaches here. Okay, so I built that up enough. Hopefully you'll have enough of the background in terms now that it'll make some sense.
What's the real state of the origin of life research? Here's the underlying theme of what you're going to see. Prebiotic chemistry, as we know it, does not move toward life. Nobody has shown a method to make these nanopure molecules. You need carbohydrates, amino acids, nucleotides, lipids. These 4 classes of compounds. Nobody has ever made these compounds with the absolute stereochemical purity that's needed using prebiotic chemistry. Never been done. Nobody has ever shown that the mixtures found in meteorites or interstellar space could be useful for synthesis, because you might have 1% of the mixture being the compound you want and 99% other things. For those of you who are synthetic chemistry, you can't do chemistry like that without enzymes. Doesn't work. Even John Sutherland, the big origin of life researcher, says these meteorites don't deliver anything that is useful because you need more constrained chemistry. Nobody has solved the mass transfer problem. This is a big problem. How much material do you need to go from A all the way to Z, the cell? How much material? You go through a synthesis, you run out of material. You got to go back and make more starting material. You've been going along now 400 million years making stuff. Now you've run out of material. Well, go back and make more in the beginning. I can't go back because I never kept the laboratory notebook. I'm just a dumb early Earth. How do you go back? How do you do this? Nobody knows how to solve this problem. Nobody has shown prebiotic route to polymerization. You can't hook the sugars together to make carbohydrates. You can't make polypeptides because of the side chain problem, and you can't make the polynucleic acids because of the 2,5 linkage in the branching problem. Nobody's made the polymeric systems that compose us. And prebiotic route. The carbohydrate, just think of it, six glucose molecules. Six glucose molecules. How can you hook them together? A, for example. No, you can hook them together in over 1 trillion ways, because there's all these different tentacles of how they can hook up. Over 1 trillion ways to hook up just 6 glucose molecules. They have open form, closed form, they have the anomeric system, and so we don't have to do this. You get the wrong polymeric structure of the cell, we'll never get a chance to live. Every disease has a carbohydrate problem associated with it. Nobody has solved the polymer stability problem when dealing with a single molecule. Time is enemy number 1. And Martin Nowak helped me calculate this on the back of a menu about a year ago. And so if you have a mole of RNA, it has a half-life, say, of 100 days, which is pretty gracious to give it. That's 2,400 hours in water temperature. What if you have one RNA that just happened to form to be just right? How long would you have to use that? That's 2,400 divided by 600 because it's 600 mer. That's 4 hours. You have 4 hours. So if the right molecule happened to form, and to polymerize, you'd have to have very pure monomer. Or else you could never get 600 mer. And now all of a sudden, all the excess materials have to come out, and you have to get all 20 amino acids diffused in from where? We don't know. It's an earlier, it's a puzzle someplace. And they have to diffuse in high purity. You have 4 hours. You can't even do that in a laboratory. It hasn't happened earlier. Nobody knows. When you're dealing with one molecule, stability is a huge problem. You say a peptide lasts longer. It lasts 13 days if you have a 200 mer peptide. Nobody has solved the problem with this functional group side chain. This kills off all polymerizations of amino acids to make polypeptides. Nobody solved that. Nobody solved the code problem. What's the genetic code? How do you come up with code for life? You have to have prescribed code to orient all these molecules. Nobody knows where that comes from. Lee will agree. He's talked about this. Where's the code? Where's that come from? Nobody has shown that you can deal with low enantiomer excess molecules and that somehow evolution they purified. No, because we know from a new phenomenon that's only about 20 or 25 years old, chiral-induced spin selectivity. This is one of those mysteries that pops up, only been known for 20, 25 years. We used to think enzymes are all hand in glove, steric effects that dominate this. That's only half the story. The other half is that every chiral environment acts as a spin valve and selects the spin. And that's why in nature you can have 2 hydroxyl radicals can come together to form hydrogen peroxide, or they can go to form oxygen plus 2 protons because they're going down a chiral environment. We never knew this. There's many other mysteries that we're going to have to solve before we can get this thing solved. I put before 10 researchers, these 10 researchers, Lee Cronin being one of them. I said, could you just solve these 5? I put before you just 5. Just make a polypeptide, not even a polypeptide, make a dipeptide. Just hook 2 peptides together, make DK 90% yield, provide a cashew. Make a polynucleotide. Make a polysaccharide. Just 2 glucoses hooked together with great chemistry for me. What's the origin of specified information? And can you assemble a cell? You answer any one of those 5, I will shut up for the rest of my life concerning origin of life and the problems with it. I'll leave you guys alone. I said it to them, I said, you got 6 years to solve it. Just solve one of them, and I will shut up. None of them sent me anything except Lee, and I'll show you what he sent me. Steve Benner said, I can solve that in an hour. I said, why don't you come to Harvard? And every one of these guys was invited here to this event to speak. None of them took it except Lee Cronin. Steve Benner said, no, I don't have time for that. I said, Lee, I will fly to your institute in Florida. You come and tell me. He said, my health and my time won't permit it. I'm flying you. So Lee Cronin wrote to me, he says, hi Jim, I don't agree with the questions. The emergence of life goes way beyond these narrow questions. I don't agree with the questions. Well, you just had a paper I showed on peptide synthesis. You just had a paper on sugars. How could questions 1 and 3 be irrelevant? I mean, you have papers on them.
And it was hard to stop it, but that's, I figured, well, you'll be saturated. Okay, so I can wrap this up with a couple more slides. One more resource to call out, and James Tour interviewed this guy on his channel. The guy's name is Otangelo Grasso. I think he's Brazilian, but he introduces himself as Swiss Italian, and his Italian his accent is hard to tell. Anyway, he's done this 3-volume work. He used AI to help him write these books, which is why some people automatically are going to criticize it because it's voluminous, and he's used AI to help support writing of it. But James Tour has read the first book, and he said, I can tell you this. I went through the whole 450, 500 pages of the first book, and it's spot on. I'm amazed. He said Tour was amazed by how much information this guy pulled together in just the first book. He hadn't read the second 2. It's called X-Ray of Life. What I thought I would do is just show you the table of contents for X-Ray of Life Volume 1. Now, I realize this is way too small to see. Let's just go to any of these prebiotic phosphodiester bond formation. I mean, that's a challenge. This is a list of challenges and difficulties that they have to overcome if you're going to have life created without the means of biological machines like enzymes and things and so forth. Formation of alternative nucleotide analogs. We didn't talk about nucleosides. There's Challenges to selective phosphorylation. I think I mentioned phosphorylation in the last talk. That's the process of creating the proton gradient, and so forth. I mean, this goes on and on. There's every one of these first enzyme mediated cells, vesicle formation and stability. There's just tons of stuff here. I don't know if I'll look at it or not, but it's impressive. And so that's the third resource I would point you to if you're really wanting to get into this topic. My point is, God has left us with such rich resources. He has not left us as he promises. He does not leave us out without the means to thrive in this world. And I think this is a case again of that occurring. So I'll leave you with a concluding thought. Slight turn, but not much. Hebrews 11:10. For Abraham was looking forward to the city that has foundations, whose designer and builder is God. And I was thinking, boy, God builds things. Look how amazing the stuff he's built here is. It's just over the top amazing. And yet here we have a real point. Obviously, God's the creator, but the city he's building right now for every one of those who trust in him, trust in his son for their salvation. That's the direction we're going then. Whose designer and builder is God. I thought that was a nice little verse to conclude. Thank you.
Okay, questions for Steve? I think I actually dated polypeptide years ago, like in high school.
Yeah. 2 L's, but yeah.
No questions. I think when you had Rob Stadler up there at the beginning.
Yeah.
And he was talking about degrading and then trying to build it back.
Right.
It reminded me, Scott used to do a presentation years ago. I don't know if you've used this recently, but he used to have the example of throwing a frog in a blender.
Yep.
Blend him up. Everything you need for life is in there.
Right.
It ain't happening. You can go this way, but you can't go that way.
Right.
So, yes, sir.
I was wondering, on that one picture you showed energy being involved in this, but what energy are you talking about, light or heat or what?
It's a great question. And for those that didn't hear it, what energy is involved in some of these reactions? And it turns out it varies. As I was looking at, and I can't say I was looking at the papers directly, Tour and Stadler go through the papers, which is very helpful to me because they'll read a paragraph and they'll say, here's what they're saying. Some of the paragraphs I do understand. Wow, that's amazing they even try to get away with that. Other paragraphs, it's over my head and they explain it very well. Anyway, the types of energy vary as far as I can tell through the steps of synthesis. What really also varies is the pH levels, the pressure levels, the temperature levels. They'll have a stage which has to occur at 87 degrees Celsius. And then the next stage has to be at 3 degrees Celsius, so like just almost at freezing. This stage has to be at 11, acidic, a very base 11. This next is at a very acidic 4.2. And these are the stages that are successive stages in the synthesis of a single molecule. So how do you get all these very controlled situations and then the types of energy? Well, Uri Miller used what was electricity, simulated a lightning strike in a reducing or methane atmosphere. But I'm sure they use whatever they can to try to get it done without the use of enzymes. And the remarkable thing is, while they're getting 1 and maybe 5-10% yields, your cells are getting 99.9999% yields in these reactions that your cell's doing constantly, keeping you alive with. The cells are remarkable and how efficient they are. And we're just not even close to being there.
Well, a cell is what they say popped out of the primordial soup that started it all. And Steve, tonight you said there are 1,000 proteins
just in the membrane.
In the membrane of the cell.
Of a modern cell, yeah.
Yeah. So that it was, they tell us there were a bunch of chemicals that somehow coalesced together to form that cell.
Yeah.
That's just, and I've read several different You put up albumin up here and showed how ridiculous it is to think that
Statistically,
statistically farmed randomly. I've read Dr. Werner Gitt said that we have 100,000 proteins in our body. I've also read another guy said there was around 50,000.
the numbers vary because they keep discovering stuff all the time.
Yeah,
Oh,
they
that
keep
was
finding them.
the last point of my agenda. The goalposts are getting further away.
Right.
Like that that chiral induced spin selectivity. This is new stuff. They're discovering more new stuff than they are solving the old stuff. We're still dealing with the same Urey results from the 50s.
Right.
And they haven't made many steps since then. And you look at all other areas of science, how they've exploded. Now we're getting so smart in all these various areas. Your origin of life is staggered or not stopped in its tracks, but it's slowed. Not that they aren't saying they're making progress, though. I don't want to get the wrong impression there. Again, if you Google it, you're going to get all the kinds of papers and things that, oh, yeah, we discovered this. The latest one is they think they know how chiral molecules actually get made chiral, how you get chiral purity through a prebiotic route. And I watched the guy's video. He's a researcher for Jack Sostek at Harvard.
Mm-hmm.
We'll hold that for future talk. It's a little contrived, but basically it's involves magnetism, magnetite. They mix it up differently. They put magnetite at the base of the petri dish where they're making these reactions, and
all these things they're doing on purpose happen by accident.
Right. You got a very intelligent person, but they're saying, yeah, this could have happened this way.
Okay, just a couple of things and then we'll adjourn. Steve has got system tracks up here. He gave us talk on systems at our last meeting. This is a track that we produced. We do sell them a pack of 25 for $5, but Steve will give you a free one here. Scott, you had something?
Well, I want to kind of go back to Carl Sagan, Carl Sagan, where he sits there and he says, hey, it's so prevalent, that in the right conditions, boom, boom, it just pops. And that's where I'm kind of at. I'm kind of at, like, if this can happen naturally, if we try to do it in the lab, this should be very easy to do in the lab, I would think. And if we're having difficulty doing it in the lab, to me, that says it is impossible to try to do this in nature. And that right there should be invalidated right there, is because it's so difficult to do. They should be doing this, to me, they should be doing this in college chemistry classes and saying, here, we're gonna do life today.
We'll create a cell today,
Boom.
this semester at least.
And we're gonna create this and that, boom. And it should be so easy to do if it happened naturally. And to me, when they sit there and say, oh no, you've got to do all this stuff, and then as he goes through, he says, look at all these problems you've got. How in the world do they make that leap? And that is a statement of faith, isn't it?
I think so. There's a paper I read. It's been a couple of years, so this stuff doesn't retain as well as it used to. It's called Dissolving the Fermi Paradox. It's based on, I think it was a physicist, Enrico Fermi, who basically said, based on why aren't we seeing life all over? Because we got hundreds of billions of stars just in our galaxy. And we got hundreds of billions of galaxies. And we have all these exoplanets. Why aren't we seeing life everywhere? Exactly. And this paper is written, it's out of Cambridge or someplace. It's written by academics. And it's called Dissolving the Fermi Paradox. Basically, Enrico Fermi was saying we should see life everywhere. It's got to be, the statistics have just got to be overwhelming that we'd be seeing this stuff. And we're not. And that's why the paper kind of went into light some of the origin of life stuff, but it took other aspects of it, physics and things. And I don't remember all the details, but I do remember the title, and I should have taken more time with it, but Dissolving the Fermi Paradox, because it does deal with this kind of idea. If this were easy, we should be able to do it. We should be seeing it everywhere. I come back to Luca. Why do you just propose one? Are you conceding something that this maybe is super, super, super difficult, and in the last 4.5 billion years life of this planet, you got one population? Maybe they are conceding that this is difficult.
Okay, so we got tracks up here. Board members, if you don't mind hanging around for about 10 minutes afterwards, we got just a short piece of business we need to do. And Zach will be our speaker next month, and your topic is?
It'll be Missouri geology. updated version of my talk from the Homestead Conference last year.
And what was it again?
It's Show Me Geology.
Show me, for those of you at home, show me geology. So it'd be geology in the show me state. All right. With that, no more questions. We're adjourned. Thank you for coming. Thank you online, those of you who watched online.
Well, sorry about that.
No, it's good.